Right, we'll attempt today to have a look at electric fields and gravitational fields, both from Module 4A2. Now, there are so many similarities between these two types of fields that it's worth looking at them side by side just so you can see the similarities and the differences. Now, gravitational fields, or G fields, a lot of our thinking comes from Newton's law of gravitation, which is this: F equals minus big G m1 m2 over r squared. So the force between two bodies is proportional to the product of their masses and inversely proportional to the square of the distance between them. And the constant of proportionality is this big G. That's the universal gravitational constant. Look it up on your formula sheet. This is the size of the force, these are the two masses involved, and this is the distance between them squared. This minus sign means that this is always an attractive force. Unless there's something significantly different about the universe we haven't yet discovered, gravity is only an attractive force. Electric fields have a very, very similar equation. It's called Coulomb's law. And it says that F is equal to Q1, Q2 over 4 pi epsilon naught r squared. Now, these three things here, 4 pi epsilon naught, that is doing exactly the same job as big G, it's just a constant. Some people replace 1 over 4 pi epsilon naught with k and just call that one constant to make the maths look a little bit neater. But here we have a force between two charges is proportional to the product of the charges and inversely proportional to the square of the distance between them. Exactly the same mathematical pattern, which is good to know. Notice the lack of minus sign. That's because this would be currently a repulsive force if the two charges are in the same direction. So two positive charges would give you a repulsive force. Two negative charges would give you a repulsive force. However, if you do end up with one positive and one negative force, we end up with a minus sign. So similar to gravity, that becomes an attractive force. Now that we've got a force, we start thinking about field strength. A gravitational field or an electric field is the area in which a force is exerted by a mass or by a charge. And we define the field strength as being the force per unit mass. We define the field strength over here as being the force per unit charge. So mass is what causes gravity, charge is what causes electric fields, and they are also what experience the forces in those fields. So it's how much force does each unit of mass or charge experience. Conveniently, you can stick that into Coulomb's law or Newton's law, and we can end up with another expression and so we've now got expressions for field strength around a mass or around a charge just in terms of the mass of the body we're looking around. So this would be the field strength around a planet of mass m. This would be the field strength around a charge of charge q. Now that gives us quite a lot to work with. But we don't stop there. We move on from looking at the field strength to talking about potential. Now, if this is my planet, we define a point we're going to call infinity. And that basically is a point so far away from this mass that it doesn't experience any gravitational force at all. Now in reality that doesn't exist, but there are places if we go far enough away we can assume that we're down to zero field strength. As you can see, this disappears quite quickly with distance. So infinity is the point where we define the potential as zero. Now what is potential? Well, potential, V, is the work done per unit mass to move a body from infinity to a specific point. Now, for gravitational fields, because they're always attractive, it actually takes energy to move something away from the planet. So anything closer to the planet is actually at a lower potential. Now the lines I'm busy drawing, which should be concentric circles, but I apparently am unable to draw circles, never mind. These are what we call equipotentials. They're like contours on a map. They are lines that show places with the same potential. So moving from infinity to here actually would take a negative amount of energy. So I might say it's minus 10 megajoules per kilogram. That is the amount of energy it would take to get there per unit mass. So it actually this body would lose energy, it would lose potential energy as it fell to that distance. Conversely, it would take 10 megajoules per kilogram to lift it up to infinity to free it from the field of the planet. We could call this one minus 20 and this one minus 30. We can do exactly the same over here, except that potential over here is defined as the work done per unit charge, of course. And if I were to have a positive charge in the center, now we always talk in terms of fields, what happens to a small test mass or a small test positive charge. Now, if I have my infinity in this diagram, so potential equals 0 at infinity, I've got a small positive test charge. It actually does take energy to push it closer to this positive charge in the center. It's going to be repelled as I try and push them together. So this would be 10 megajoules per kilogram, 20 megajoules per kilogram, 30. And so in this diagram, I've got a series of positive potentials, positive equipotential lines, as it takes more energy to push that small test charge closer. Now, in practice, what you end up doing quite a lot is using this equation to work out the work done, the amount of energy that's needed, the amount of work you've had to put in to move something from one equipotential line to another. So to bring a charge from here, so to bring another proton, say, and to push it into here, how much work would it take? Well, it would take VQ. So you multiply the charge of what you're moving by the change in potential that you've moved it across. Similar here, I want to move something up. I take it from minus 30 to minus 10. Well, that's gone up by 20, so my change in potential will be 20 times whatever mass it is I'm moving, and that would tell me how much work I had to do to move that. And we can also rearrange, we can substitute this equation and do some fiddling around with this force equation, using the idea that work done is force times distance. And again, it would take a little bit of calculus to derive entirely, but what we end up with is an expression for potential in these forms. And notice that these potentials are not proportional to r squared, to 1 over r squared, they're just proportional to 1 over r. So this follows a different pattern to the equations we've had so far. Now, one common question that comes up is that they will give you two different masses, and they will ask you about something that's going on in the middle. Now, obviously, in between these 2 point masses, there's a gravitational field from each mass. And we could do various things with that, but one of the common questions is to ask, where is the gravitational field strength equal to 0? And so somewhere along this line. Now, there are various ways of solving this, but the easiest thing to do is to say, well, my gravitational field strength from M1 is equal to G M1 over R squared. And for gravitational field strength to be equal in the middle, and gravitational field strength is a vector quantity, well, that's got to be equal and opposite to G M2 over R squared. The two field strengths have to be equal and opposite, pulling in opposite directions. Now, this very conveniently means I can get rid of those constants, and I can end up with a very, very simple expression that tells me that the ratio of distances between them is equal to the root of the ratio of their masses. That's really, really convenient and easy to use. Sometimes we're not interested in the field strength between two points, we're interested in the potential between 2 points. Now, in this case, if I've got one positive charge and one negative charge, it's actually not possible to have a zero field strength in the middle, because this would be repelling a positive charge and this would be attracting a positive charge, so both field strengths would be acting in opposite directions. It is, however, possible to have a point where potential is zero. Now, to find that, we have to do a very similar thing. We have to say, well, V equals Q over 4 pi epsilon naught R. Now, this means that if I look at this for Q1, that's got to be equal to the potential, minus the potential from Q2, 4 pi epsilon naught R2, and again that constant cancels, and I end up with this expression that Q1 over Q2 is equal to R1 over R2. And that very conveniently says that the distance, the ratio of distances from those charges is the same as the ratio of their charges in order for the potential to be equal to zero. And that is a really, really convenient equation to be able to use. Now, there is one extra little bit for electric fields which we don't deal with for gravitational fields. On a large scale, so looking at a planet, we will always talk about a radial field pattern which follows these rules. We do approximate that to being a uniform field over a very small distance, so anything up to perhaps 100 kilometers or so. We can say that's a uniform field on Earth. We can assume the field lines are parallel and the field strength doesn't change. With electric fields, we can actually make an area of properly uniform field strength just by having two parallel plates connected up to some circuit, and we put a potential difference across them, and in between those two parallel plates we will have uniform electric field, and it will have field strength of the potential difference between them in volts divided by the distance between them in meters. That tells me that my field strength can also have units of volts per meter. Just hinting back over here, this is my expression for potential. If this is volts per meter and this was measured in volts, then I have another equation for field strength, and my other equation for field strength is that it is equal to the potential gradient, the rate of change of potential with distance, or if you like, dV by dr. Over here, that becomes important as well, that this can also be equal to a gravitational potential gradient, which is a change in potential over a change in R. It's worth bearing those things in mind, because sometimes you will be working with potentials and then we'll be asked about field strength, and this is the easiest way to get from potential back to field strength in both cases. But particularly for electric fields, keep an eye out for parallel plates, because parallel plates mean you can ignore all of these equations in which the field strength and the force experience diminish with distance, and you can assume an area of uniform field.